Good evening, and thanks everybody for joining. My name is Doug Saratori. I am the principal consultant at Parallel 42 Systems, and I'm also a GIS hobbyist. I've got plenty of experience with databases. I've been working with databases, primarily Microsoft SQL Server, for the past 20 years. What's really exciting about this particular topic is that it's an opportunity for me to connect one of the things that I do professionally with a hobby that I have. And I've had the opportunity to work increasingly with spatial data recently in SQL Server, and I thought I'd share what I've learned. So the first thing that we should talk about is what is spatial and geospatial data. So spatial data represents objects, whether they be points, lines, polygons, or a combination of any of those in a geometric space. Geospatial data is more specifically represents objects that are located on the surface of the Earth. So the main difference between the two is that the entire universe of geospatial data is finite. It's finite because it is contained on a globe, whereas spatial data exists on an infinite plane. And we'll get into some of the details about how SQL Server deals with both of those types of data a little bit later. There are a few things that you should keep in mind when you start working with this kind of data. Where can you find geospatial data? Well, the best place to look is your local or national open data portal. Lots and lots of open data is available out there, whether it be something related to elements of your community, or whether it be data on a bigger scale. And open data portals are a great source for GIS data. Tonight, we'll be doing a demo with data that I have retrieved from open data portals, one from my local community, Windsor, Ontario, Canada. We'll be looking at the boundaries, the political boundaries of the city, and doing a little work with that. And we'll also be working with some data across Canada, some data related to federal electoral district boundaries, as well as postal code boundaries. You can also source GIS data from the users of an application that you have written or are hosting, users' location data, the travel of users as they use your application. That type of data also can be used in this format. And finally, digital map providers like Google and OpenStreetMap are also an excellent source of data that you can use with SQL Server in this way. GIS data comes in a number of source formats. I've listed a few here. There are literally dozens of different ways that GIS data can be encoded. The ones that you'll encounter most often are the ones that I've listed here. Esri shapefiles are really quite universal, especially when you're dealing with open data portals. And the reason for that is that ArcGIS, which is an Esri product, is the most common GIS tool that is used in industry, used by governments and so forth. I use an open source program called QGIS, which you can download for free. It's very powerful, and its native format is also Esri shapefiles. GeoJSON is one of the most common ways that you'll encounter spatial data on the web. You've got an example here on this slide of what GeoJSON looks like. This is a data set that I built of different legendary monsters in Canada. So you can see the way that that data is encoded in the JSON format. And I chose JSON for my example because it's pretty easy to understand. It's nicely structured, And it gives you an idea of the basics. So GIS data, not only does it contain geographic information like points or lines or polygons that will be placed on a map, it also contains the properties or attributes of that data. So in this particular example, you can see that the name of the location, the province in Canada where the monster is found, and the name of the monster or monsters are the properties of each specific feature. Every GIS program uses or employs similar data, but it encodes it in a bit of a different way. KML files are the format used by Google Earth and other applications, so you will quite often see that. And finally, the last one I want to mention is well-known text. I've marked that with an asterisk because well-known text is not actually a file format. It is a format for encoding geographic data in text. So where you'll often see well-known text data is in a CSV file. So there'll be a comma-separated values file, a spreadsheet that you would open in Excel or some other tool like that. And one of the columns will contain the text representation of the GIS data. The other thing that's important to know about well-known text is that this is the format, well-known text along with its binary cousin, well-known binary, WKB. These are the formats that SQL Server wants to receive GeoJSON or JSON, sorry, that it wants to receive GIS data. So these formats are sometimes needed as an intermediate format. And we'll talk about that a little bit. We'll walk through that process of taking data from some random source format of GIS, moving it into WKT, and then moving it into SQL Server. I mentioned at the top of this discussion that there are two types of spatial data in SQL Server. These are the data types that you will use in your queries. Geometry data type is the flat representation of geometric data on a infinite plane. And geography is the round Earth coordinate system. You can use both, but there are some caveats to think about here. The round Earth geography data can be a little bit finicky to deal with. And one of the main things, the main challenges that you'll find, and I encountered it in setting up the demos for tonight, is that on a finite globe, when you define a polygon, it's not obvious which side of that polygon is the side that should be enclosed. Because you're on a finite globe, either the inside or the outside of that polygon might be what you actually want to be the inside. So there are different ways of directing the software that you're working with to understand which you mean, which way that it should understand that polygon. And we talked about some of the different source formats a moment ago. One of those formats, the most common one that you'll encounter out there in open data, is the Esri shapefile. And Esri shapefiles use the right-hand rule, which means that you start with your first point and then you define the polygon moving clockwise. Well, that's fine, but SQL Server uses the left-hand rule, which means that SQL Server wants those polygons to be defined counterclockwise. And this can create all kinds of problems when you import spatial data into SQL Server. There's trade-offs here. Obviously, there are benefits to using the round Earth coordinate system. One of those benefits being that you can do so without distortion. Transposing coordinates that represent a location on the Earth into a flat plane is going to result in some distortion, more or less distortion, depending on the projection you use. More on projections in a moment. So one thing that I recommend, especially if you're just first playing with this type of data in SQL Server, is that the geometry type is a lot easier to work with for that exact reason. That you'll find that no matter which way that your source data defines those polygons, left hand, right hand, or using some other rule, SQL Server will interpret the intended polygon far better if it's using the geometry type. It's far more reliable. And I encountered this problem in dealing with some of the demo data. And there are tools and techniques within SQL Server that you can use to reorient the objects in your spatial data set. However, they're not foolproof, and they can run into you can run into significant problems. One of the other challenges, just going back to file formats for a moment, one of the other challenges that you can face is the limits on character count when you are trying to move from one format to another. I encountered this in trying to create a well-known text file from the map of Canada, the map of federal electoral districts in Canada. And what happened is there was one particular electoral district that the geography is so complex that it actually overflows 8,000 characters, which results in truncation. So you end up with a polygon that doesn't close, which is a problem. So I worked around it for this case, but there are some things to think about when you are trying to move your geographic data into a format that is going to be consumable in SQL Server. And just keep those things in mind when you do your own work. So within those two types, the spatial type and the geospatial type, the spatial type being geometry and the geospatial type being geography, within each of those two spatial types, there are a number of different objects that represent different ways to define a point, a line, or a polygon, or a combination of those things in the database. So there's a nice chart here. This chart is provided by Microsoft, which provides a little taxonomy of the different spatial data objects that are available. The blue ones are the ones that are actually instantiable in SQL Server, okay? So the items in yellow are not objects that you can actually create an instance of in SQL Server. Just to walk through these fairly quickly, the point should be self-explanatory. It is a point on the map, a single point. If you think about a specific latitude and longitude coordinates, one single pair of coordinates, that would represent a point. It has no dimensions. It just simply represents a single point on the map. Then beyond that, a line is defined by multiple points. Okay, you need a starting point and an end point and any number of points in between. SQL Server spatial objects also support curves. So the circular string and compound curve data objects, they allow you to define a curve by defining the two endpoints and the point in the middle, and that is how you define a curve segment. Then we get into polygons and curved polygons, which are enclosed shapes, okay, consisting of multiple points with a common start and end point. A curved polygon, again, uses that curve notation to allow you to define a curved object rather than just defining straight lines. Then geometry collections are collections of these specific object types: multi-polygon, multi-line string, and multi-point, each of which is pretty much what it says on the box. It is a collection of objects of a particular type. So that's a extremely fast introduction to the different objects that are available. And I'll show you how you work with these objects when we get into the demonstration. SQL Server gives you a number of methods that you can execute on a spatial object. These are some of the most useful and commonly encountered ones. And I think this is one of the things that gives you so much power, and one of the things that's so valuable about working with spatial data in SQL Server is the ability to work with data. And if you think about a database that is, for example, the back end of an application, you can work with this data programmatically within your database and get all kinds of answers about it. You can, for example, use ST intersection, which we will be using tonight, to get an object that represents the intersection of two other spatial objects. So if you have two lines that overlap, you can use ST intersection to find the line segment that consists of the overlap. ST distance returns the shortest distance between two spatial objects, and so on. ST intersects, as distinct from ST intersection, is really useful because that returns basically a 1 or a 0. So it gives you a true or false answer on whether or not two objects intersect. And you'll see how we use that later on. And there's a number of other methods that I've listed here. You can see them on the slide. They're all quite interesting and useful, and there are a whole bunch more. If you check out the Microsoft documentation and books online, there is a list of a few dozen possible methods that you can use on spatial objects. Okay, so we've talked a little bit and oriented on some of the basics, some of the basic tools and resources that are available to us in doing this work. And now let me show you the process of importing GIS data into SQL Server. So I'm just going to change my share. Just bear with me for a moment. First, we're going to take a look at the GIS tool that I mentioned earlier. This is QGIS. QGIS is the open source tool that allows us to work with many different GIS file formats. Specifically, it's useful because we can process Esri shapefiles with it, but it handles many other formats. And one of the nice things about QGIS is that it's a graphical tool that you can use to look at your data before you import it, before you work with it, visualize your data. And you also can use QGIS to change the format, to save this data into a different format. And I'm going to walk you through that. There are other tools that you can use to do that. There are command line tools like OGR to OGR that allow you to move GIS data from one format to another. But QGIS is a nice graphical tool. I'm pretty familiar with it, so this is what we'll use. So we've got what we're looking at here are the political boundaries of the city that I live in, Windsor, Ontario. There are 10 wards in Windsor, and this is the way that they look when you look at them on the map. This layer, okay, is defined over here, and you can see there's some details here. So the EPSG 4326, that notation that you see there is pretty important, because what that's defining is the SRID, the spatial reference ID of this GIS file, okay? And that's important because it defines the projection, the way that this data will be projected onto the map. There are a number of different ways that you can project data onto a map, onto a globe rather, and the different formats serve different purposes. Some of them are extremely accurate, but only accurate in a narrow piece of the globe. And you'll often find, for instance, that municipal data portals will use a will use a spatial reference like that because it produces an output that is more highly accurate in that specific geography. On the other hand, if your data set is larger, if it crosses time zones, it's bigger than one specific small location, then a different projection might be more useful. The one that I'm using here is the latitude and longitude. This is WGS 84, SRID 4326. This is a very common format, and it's one that's really useful because the data is represented in degrees of latitude and longitude. When you output this data as a text file, you will actually get your coordinates in latitude and longitude, which is useful because it's pretty intuitively understandable by humans, unlike the coordinates in other projection systems. Okay, so we've got this layer and we can export it. Okay, looks like I'm going to have to share this little window separately. Perhaps I'll share my whole screen so that you can see this. Let's try that. Okay, that might be a little bit better. So now you can see the Save As dialog box. So basically, we've got we can select a format. There are a number of different formats that QGIS supports for exporting data. We're going to choose CSV. I'm going to call this, whoops, need to put it somewhere besides System 32. So we'll put it on the desktop. Okay, words. All right. Okay. There is our projection right there. Okay. We're going to export all of the fields in the associated attribute table. Okay, automatic geometry types. Now, here's a couple things that we need to do that are specific. We want to export that geometry as well-known text. So remember, well-known text is a format for defining geographic data. However, it is not a file format to itself. So we are going to create a column in our CSV that contains geography represented as well-known text. Okay, I think everything else here is going to be okay. We will not add the save map to our file. All right, layer exported. Okay, now we'll move over into SQL Server, SQL Server. Okay, and we'll import this data. So I've already created a database. Okay. This database is empty, but it is here to receive the Word data. We're going to use the import wizard. Okay, this is a pretty common tool. I'm probably going to have to share my whole screen once again. We'll do that. There we go. Okay. So the import wizard, there we go. The import wizard allows us to take data from multiple sources and import them into SQL Server. If you're not familiar with this, hopefully this brief demo will give you the information that you need. This is a pretty handy tool, and if you are moving data, slinging data in and out of your database server with SQL, you will use this tool quite a bit. Our data source here is a flat file. Okay, we need to specify that source file. Okay, that is on our desktop. There it is. We need to identify the text qualifier. Okay, everything else here should be okay. We can take a look at a preview of our data. looks okay. Clicking on the advanced tab here, we have a chance to define the column names and the data types that we're going to import into SQL Server. SQL Server is typed, obviously, like all relational databases. Every column has to be a specific type of data. One of the things that's really important here is to make sure that you are choosing the right data type and the correct size for that data type. When importing WKT information, you want to use the text stream data type. That is going to allow you to have a more or less unlimited amount of data in a single column, which you need because WKT data is pretty verbose and can take up a lot of space. Okay, all of these others don't matter so much. One thing that I will mention is that if your source data is Unicode and contains special characters, then using the Unicode string is just going to make your life a little bit easier. Okay, this is a pretty simple data set. In fact, I think that is a numeric type, not a text type, but it won't hurt a thing to make them all Unicode. Okay, all right, once we've defined our source data, then we have to define our destination. In this case, I am going to put it on the local SQL Server here on my laptop into the wards database. Next. Okay. SQL Server is suggesting that I use a table called wards, which sounds great to me. Okay. Now we finish this up. And if I've done everything right, we're going to get success. Okay, great. So now we have imported our text file into our database. So let's see what that looks like. Okay. Change to my wards database. Okay, so now we have a table with the attributes and the geography information in WKT format. Here it is, just what you thought it might be, a bunch of polygons defined by a series of points in latitude and longitude format. This is good as far as it goes, but it is not yet SQL spatial data. If we refresh our database and we take a look at the table definition for wards, we look at the columns. Okay, you can see that WKT is in a text data type along with all of the other columns. So that's not going to work for us in terms of being able to do any geospatial stuff with it. So the first thing that we have to do is we have to add a column to our table to contain the geographic data. Okay. All right, here is our table editor. We're going to call this column Geo. And I think I gave you a good rundown of the geometry versus geography data type. We're going to use geometry here. For our purposes, there's not much difference between the two in this application, so that should be fine. Okay, go ahead and save that. And now, if I select the rows from my table, we've got a Geo column that has a bunch of nulls in it. Okay, so the first thing we're going to do is we need to update our table. Okay, and what we're going to do is we are going to use the geometry method, geometry from text. That's the source column, okay? And that is the spatial reference ID that I mentioned before. We want this to come in the latitude and longitude format. So this quick little update statement will basically take the text representation here and turn it into a geometry object that SQL Server can understand and work with. Okay, great. Now, okay, so now when we execute our select statement and look at all of the columns in our table, we can see that there is now binary data in the Geo column. We also have a new tab in our results set, which is the Spatial Results, and you may recognize that map because that is the map of the wards of Windsor. So now we've got our data in the format that we want, in the geometry format in the database. That's the import process. Okay, so a couple of things that I want to demonstrate for you. First, let's look at these wards with their ward numbers so I can orient you all. There we go. So this is Ward 1. This happens to be the neighborhood that I live in. And what I want to do is use a query to find out what's the furthest ward away from the ward that I live in. Obviously, we're looking at the map. You know what the answer will be, but I'd like to see and show you how we can ask SQL Server to do that for us. Okay, so. Okay, so we're using top, and I specifying top one. We only want the first result from this query. Okay. And we are going to use the order by clause to define the order that SQL returns rows in. So by using the order by clause, we can control the order that rows are returned. And in that way, we can make sure that we get the right one first. Okay, Geo is the name of our column. And we can use the stDistance method. Okay, with a little subquery there, and we'll specify that we want that order by to be descending, which means we're going to get the highest result first, which is the greatest distance. So just to walk through that one more time, select the first row from the wards table, order it by the distance, and we are then specifying a subquery inside of our method call. Okay. And so that's why you see these double brackets. Okay, we've got the first set of brackets are there for specifying the parameter of the method. The second set of brackets are there to specify the subquery. Whoops. And if I execute that subquery, okay, you may recognize that. That's word 1. And now I'll execute the whole thing. And there we go. The furthest ward from my ward is Ward 7, represented by Councillor Jiwin Gill. And there is the spatial result. Okay, some other things that we can do here. Okay, so we can use stArea to identify the area. Okay, the area of each ward in the city. Now, this is returning us the area in whatever you call that specification of latitude and longitude. Okay, so degrees, I guess. So this is the area in degrees and minutes and whatnot. Not entirely useful. Depending on the spatial reference ID that you use, you can get your area back in different units. But these are the units that we get given the data type we've chosen and the spatial reference ID that we've chosen. Okay, something else that we can do, we can use the ST-centroid method to just get the center point of each ward. So what do those spatial results look like? Not too easy to see, but what you're looking at here is a set of 10 dots, 10 points, okay? Those points are the center point of each of the wards. Another handy method, okay? One last quick demo of this, and we are going to now get only the boundary of each ward. Okay, so rather than getting the polygon that represents the area of the ward, we are now getting back lines representing only the boundary. Lots of neat stuff that you can do with geometry and geography data types in SQL Server. Okay, so let's go back to our slide deck. Okay, there's the last thing that I want to show you tonight is the, sorry, I think there's something kind of hanging over the screen there. The last thing I want to show you tonight is how we use the tools that SQL Server provides us to relate different types of spatial hierarchy to one another. Okay. Non-strict spatial hierarchies is apparently the term to use for this type of relationship. This is something that I found out about that term by doing some research for a project that I'm working on, in which I face this problem. And it's a really common problem in GIS work. We have two sets of geography. So in this case, what you're looking at here on the slide is the heavy lines represent electoral districts in Canada. And those dotted lines represent FSAs, which is a forward sortation area. In Canada, that means that's the first 3 digits of your postal code. The FSA represents a reasonably large geographic area, which is still smaller than an electoral district in most cases. Not every FSA is smaller than an EDA, but most are. And not every FSA is contained 100% inside an EDA. And this is where we run into challenges. The demonstration that I'm going to show you tonight, we are going to take data that is represented at the FSA level. This data is the recipients of the Canadian Emergency Benefits, CERB, which was used during the pandemic to support Canadians who were not able to earn an income for whatever reason. We have CERB data for Canada by FSA. This is a fantastic set of data that the federal government has provided, giving us demographic breakdowns of the recipients of CERB by postal area. And in our case, we're just dealing with the count of unique individuals who received CERB. So that's great information, but it's a very common thing to want to know which political boundaries received more or less. How many people received CERB within each electoral district? We don't have that data. That data is not published. So how do we use the spatial tools in SQL Server to relate these two hierarchies so that we can get a reasonable estimate of the number of recipients within each electoral district? And that's what I'm going to show you now. Okay. I don't see any questions in the chat, so I hope everyone is following along fairly well here. If you do have a question, please feel free to drop it in the chat and I'll do my best to answer it. Okay, So here we have our SQL Server Management Studio window once again. And before this session, I have loaded a database called EDA FSA with 3 tables. One is the electoral districts table. Okay, this table, this is probably going to look pretty familiar. This is imported from a CSV that I exported from QGIS, and it contains, well, let's take a look at what it contains. I did mention, oops, we're in the wrong database. I did mention that there are some challenges working with QGIS to get this data. So for the purposes of this demo and to make my life easier, I restricted myself only to the province of Ontario. So we are looking right now at a table that is showing the electoral districts in Ontario. There is the number, the federal number that identifies the electoral district. Here is the name of the electoral district. Here's the name only in English, the name only in French. Okay, the identifier for the province, the name of the province, and there's the geography of the province. So if we look at the spatial results, this is running off a database on my laptop, so it is going to chug a little bit. I'm just going to give myself a little more room here, but it is going to chug a little bit on some of the larger spatial queries. So here you see the map of the province of Ontario broken down into electoral districts. So our part of the world happens to be way down here. And there are the familiar boundaries of all the electoral districts in our region. Okay. We also have a table representing the forward sortation areas in Ontario, the FSAs. Okay. Let's take a look at that. So the first 3 digits of the Canadian postal code is in the column CFSA UID. There is the province UID and the province name, okay, just like in the electoral districts table. The reason that these column headers look familiar is that they are both sourced from data provided by Statistics Canada. Okay, and then finally, the third table in our database is the CERB data, the actual emergency benefit data itself. And what you can see here is the Canadian province, the code for the Canadian province, the ID of the FSA, and the count of unique beneficiaries of the emergency benefit in that particular FSA. So some of these are null. They're the data set that is provided by the federal government isn't perfect. Some of the beneficiary counts are represented by X's in the source data. Presumably those counts are either not available or there was some problem with them in terms of producing our data set. That is a limitation of our data. We're just going to have to live with it. Okay, so I've already done the work of loading up all of these tables and loading the geometry data type column geo with the shapes of all of the FSAs and EDAs. So we've already done all that work. So the thing that I'm going to show you now is the work that we can do to relate these two different geographic representations to each other. Okay. So we'll start. We are going to write a query. If you're not familiar with SQL queries, there are a couple of videos on the YouTube channel for our data podcast, Mean, Median, and Moose. That's where this one will live. And there are a couple of videos that give you a good grounding in the basics of writing SQL queries. So if you get a little lost here, there are some resources for you to refer to if you'd like to. So I am going to just specify my from clause here first before we get into the details of our select list. So I'll just leave an asterisk there for now. Okay. We have the FSAs table. I'm going to alias it with an F so that I don't have to type FSAs every time I'm referencing that table. And I am going to join it. I'm going to use an inner join. Okay. And we are going to join the electoral districts table, which we will alias E. Okay. And when you join two tables, you have to specify which column in each table should be used to connect them. Typically, the choice that you use is some identifier, an ID, often an integer that represents a key that is foreign to one table and the primary key in another table. That's typically how you join data in a well-constructed relational database, but there are other ways to join data. The only thing that we need to be able to do is we need to be able to provide a true or false some kind of equation that is going to result in a true or false response, which is how SQL Server is going to filter those elements. So the question that was asked, can you create interactive maps between QGIS and Microsoft SQL Server Management Studio? And the answer to that is no, not to my knowledge. QGIS is not really a tool for creating interactive maps, and neither is SQL Server. SQL Server is good for storing this data in a way that you can retrieve fairly quickly. You can do some cool operations on it quickly, as we're looking at. But if you wanted to create an interactive map, you would want to use a tool like Mapbox to surface a map on a web page or some other type of tool to create. There are similar types of libraries for mobile application development as well, but you could use a tool like Mapbox to create a web application that consumes the geography information from your SQL database. And if you're interested in learning more about Mapbox, we also have a tutorial on our YouTube channel about doing that. Okay. So we were talking about how we're going to join these two tables. So they do have a couple of columns in common, but nothing that's going to be useful to us for our purposes. There is no key that relates these two tables to each other. The closest that we get is they each have a columns identifying the province in Canada. That's not really going to do it for us, because what we want to do here is we want to connect these two tables based on whether or not the FSA is contained in or partially contained in the EDA. Okay, so the way we do that is we join them on the Geo column. Okay, so just take a look at that. So we're using the spatial object method st-intersects that I talked about a little while ago. And we are using it to ask SQL Server to determine whether or not the electoral district intersects the FSA. Okay, and if they do, then those two rows should be joined together. Okay. Then what I've found is that is useful, because sometimes you could end up with two pieces of geometry that intersect one another because they have they share a common border, for example. So that line that represents the border of each polygon, that line intersects somewhere. Some point on that line has an intersection because the two objects share a common border. That's not useful to us. So we need to just narrow it down a little bit. And the way that we do that, now this is a complicated little bit of code here. So we'll walk through it. We are rounding off, okay? We're using the round function of SQL Server to round this off to 8 decimal places. So that's what that outermost set of brackets is doing. We are now using the ST intersection method, okay? So we are getting back from FSAs the polygon that represents the intersection only between the FSA and the EDA, okay? So, and then we want to get from the result of that method, from that polygon that represents the intersection, we want to get the area. So we'll use the ST area method. And then we're dividing it by, straight up dividing it by the area of the FSA. Okay, so if the intersection of the FSA and the EDA, the area of that divided by the area of the FSA itself, okay, is greater than 0, then it's worth thinking about. Then it's worth working with, okay? So I can execute that. And what we're getting now is a set of combined data, all of the columns from both tables, showing which EDAs intersect with an FSA. So we could there we go. We can make that a little bit nicer, and you can see that that's taking some time to execute. So I'm just going to cancel it and get a little bit of a nicer representation. So here we have a nice little list. Here's the federal electoral district, and here are the FSAs that represent at least part of it. Okay, so we've gotten somewhere. We now have, we can now understand which FSAs are part of an electoral district. So the way that you could now do the work that we talked about, which is to figure out how many people received SERB in each electoral district, is just eyeball it. Eyeball the map and you know, try to figure out which of these FSAs are going to be significant. But we can do a lot better than that. So I'm going to add some columns here. Okay. We are going to also return, and that should look familiar because it's basically the same construction that we are using to limit our results. Now what we want is the percentage of intersection between these two geographies. Specifically, we want the what percentage of the FSA, okay, what percentage of the FSA is the intersection between this FSA and a particular electoral district. And the reason that we want that is we want to be able to use that intersection percentage to give us a rough estimate of how much of the population from that FSA we should attribute to that EDA, okay? So we can do that. And it's not, obviously it's not a perfect method. Human beings are not evenly distributed between within an FSA. There are going to be denser and less dense parts of forward sortation areas. So it's not perfect, but it's a lot better method of estimating than eyeball. So within that constraint, this will give us a far more accurate answer. So here we go. Dufferin-Caledon, that electoral district has these 7 FSAs in it. 5 of those FSAs are completely enclosed within the riding, which is another word for electoral district for the non-Canadians who are watching. And these other two FSAs are partially contained within the riding of Dufferin Caledon. And they, that they are 9.2% and 72.5% within that FSA. So let's take a look now, just for fun. I'm going to add to our where clause here. Let's see where else. Oops. Let's see where else L0N intersects. Okay, so here we go. L0N is within the ridings of Simcoe Grey, Dufferin Caledon, and Wellington Halton Hills. And there is the intersection percentage for each of those electoral districts. That is the share of the FSA that each electoral district should get. So hopefully you can see where I'm leading here. We are now going to apply that intersection percentage to the population, okay, to the population in our SERB column, the unique beneficiary count. We're going to apply that intersection percentage to get an estimate of the number of SERB beneficiaries within that specific chunk of the FSA, and then we can aggregate those to get an estimate of the number of unique beneficiaries in the riding. So we are taking hard data that is at one aggregated in one geographic boundary, and we are now using the spatial tools of SQL Server to give us an estimate of how to convert that into a different geographic boundary. Okay. So what does that look like? Okay. So we are taking the unique beneficiary count from the SERB table, this column right here, and now we are multiplying it by that intersection percent. Okay, you can see that this looks pretty similar to that. The only thing I did was calculate it to fewer decimal places, but we'll just change it to 8 so it looks a little nicer and they all match up. And now if we execute this query, whoops. Did I forget to do something? I did. I forgot to join the SERB table. So pretty tough for SQL Server to be able to do this work without having all of the tables we need data from specified. So we will join SERB on okay, so we're using, in this case, this is not a kind of a fuzzy join like we're using to find intersecting electoral districts. This is a join on specific data. We are joining the forward sortation area column in the SERB table with the CFSA UID column in the FSA table because they represent the same data in the same format. The text ID of the 3-digit FSA ID. Okay, so with that information, okay, so we've got a problem here because we are trying to sum up the data, and the reason that we're summing this data, the intersection of the we're summing up the intersection of the FSA with the EDA is because we actually want this data at the EDA level. So one thing that we will not be able to do is list the FSA any longer because we need to now group this table or result set so that it is at a higher level of aggregation. We are going to group it by the federal name of the electoral district in English. So what we're doing now, using the group by clause, we are telling SQL Server that what we want is one row back for every electoral district. And now we're actually not going to be able to return this column either. Every other column that is not represented in the group by clause now needs to be an aggregate function, because we want the sum of the proportional number of beneficiaries in each piece of the FSA that is inside the specific EDA that it's being joined to, right? We want to sum those all up so that we get one number per electoral district. Okay, so we can execute this guy. And what we'll get back after SQL Server thinks for quite some time, because this is a reasonably complex query and a lot of chugging it has to do to process all of those individual maps. And here we go. We now have the federal electoral district and the proportional estimate of the SERB recipients for that riding. So we can now answer questions like, which federal riding had the most SERB recipients according to our estimates? And it's always important to remember that we're now dealing with estimated data, because we can't know the exact number of recipients in an EDA. If we could, we wouldn't have to do, we wouldn't have had to do this work. So this will just take a few more seconds. Okay, there we go. And now we know the in Ontario, which federal electoral districts received the most in terms of the number of recipients of the emergency benefit. And it's no surprise, you know, the top three are all in the Greater Toronto area. No surprise, you've got in the GTA, you've got lots of folks who work in relatively low paying service jobs in the city of Toronto. Maybe they can't afford to live in the city of Toronto themselves, so they live in one of the neighboring suburbs, and they commute. So these would be the folks who would be the most vulnerable to a lockdown or shutdown because of the COVID-19 pandemic, and therefore they had the highest number of recipients. Not a big surprise. Anyway, it's pretty interesting little data set. It's not something that is available out there, and this is the method that we use to synthesize it. Okay, and that is everything that I wanted to share with you and show you about geospatial data in SQL Server tonight.